Thank you. I'm very happy to be here. Thanks for the invitation to give a course here on the subject which I was working on for some time. And I think it's interesting especially in the commutative or commutative Noetherian case, which was for a long time neglected because the people looked only at finite dimensional modules. As we will soon see, there are no finite dimensional or finitely generated examples to the theory from the point of view I will speak about. So it's happy to be here to celebrate with Roger and Sylvia. They're 151, I understand, or not yet, it's 150 birthday. I wish them success. I think they're very fine mathematicians and great personalities. I think all of us know, so I don't have to tell stories or repeat these again. And the talk is mostly on slides, but I will also use the blackboard for the proofs or some explanations. And the handout of the slides is available. Thiago has them, so maybe he will put them on the web page. I don't know. So you don't have to write write what's on the slides. And the tilting theory I will speak about, my talks will concentrate on the general notion of a tilting module and tilting class. The particular emphasis is that the modules are infinitely generated, and they are the interesting ones in the commutative case. So the first lecture will be in this general setting with examples in the commutative case, and then the second lecture will give you a very concrete. We'll look at the concrete setting of commutative Noetherian rings and classify the tilting and cotilting classes. The interesting thing there is that it's easier to do the dual case, which normally is more difficult because the objects are pure injective, so you have some help. And then via Auslander-Bridger transpose and other tricks, you go back to tilting. So that's why we will actually introduce the cotilting setting, otherwise it looks like a formal dual, but in fact it's a very important tool. And the last lecture, if we get that far, is an example of the application of this theory to generalizing a result by Reynaud-Grusson on the locality of the notion of a vector bundle in algebraic geometry. So the talk today will consist of several, I think 4 parts. The first is just the modules and classes to be introduced. And then there's a major result which says that though the modules are infinitely generated in the interesting cases, there's a point that the classes can be defined using finitely generated modules. You just replace the single tilting module by a set of finitely presented, and this has very nice consequences for the structure theory. Then I will give one application to the computing the finitistic dimension of Ivanaga-Agharnstein rings in the not necessarily commutative case, just to show you that what you can do with this finite type theorem. And then I will speak briefly on the relation to approximations of modules, which is one of the topics which was developed over the past 10, 20 years. So the tilting theory goes back to 1974. I think was the first results in the setting of finite dimensional modules over finite dimensional algebras. But the theory was developed gradually in many directions. So this is the direction which goes to infinitely generated modules, and particular it makes, as I said, it's interesting in the commutative setting. So the definition is essentially the same as it was in 1974, except you allow, or maybe a bit later, you allow for infinitely generated modules. So the setting is you have a ring and any ring, associative ring with unit, and a finite number, and you say that the module is n-tilting if it has the following 3 properties, denoted usually by T1, T2, T3. T1 just says that the projected dimension is bounded by n, so it has an at-R resolution, if you want, of length at most n. The second condition is there are no self-extensions, and even stronger, in the stronger sense, that the x vanishes of T and the direct sum of copies of T vanishes for all xi for all I at least 1. So this is sometimes understood as a strong splitter property. And then the T3 condition is sort of dual to the T1. It says that there's this approximation of the regular module by the modules in the class at T, where at T means is the class of all direct sums of possibly infinite copies of the module T. So this is, you can say that in other terms that the regular module has an at T co-resolution of length at most n. So this is the definition. Now a tilting module is just n tilting for some n. So there are two useful notions, particular kinds of tilting modules. The first one are called good, and this is, I think this goes back to Silvana Bazzoni in the 2005 maybe, and that just needs, good means that in this condition T3 you can replace the direct sums of possibly infinite copies of T by direct sums of finite copies of T. That's the small r, the usual meaning, the usual notation. And classical is the tilting module which is finitely generated, well, or more precisely, strongly finitely presented, means it has a projective resolution consisting of finitely generated projective modules. And the resolution is finite, of course. So it's the same as finitely generated for Noetherian rings, is the same as finitely presented for coherent rings, or right coherent, but otherwise it's a stronger notion than finitely presented in general. So for example, the zero tilting module, if you look at the definition, is nothing else than the projective generator, not necessarily finitely generated. Just if that comes from condition T1 and T3, T2 is automatic. So this is always good by definition, and it is classical if and only if it's finitely generated. So it's a progenerator in the sense of Morita. And we will say that two tilting modules are equivalent if the at classes are the same. And the lemma, which is an exercise, but maybe I should at least hint how to do the exercise. Any tilting module is equivalent to a good one. So why is that? So in other words, you can, up to equivalence, you can impose the make the condition T3 stronger. And the proof is essentially, let me just hint for this lemma. So, oops, the hint is as follows. First, use the Eilenberg trick to replace at T by sum T. Now at T is direct sum ends of copies of T. Sum T is just direct sums of copies of T. And why can you do it? Because if you have a module which is a sum end of some direct sum of copies of T, then the Eilenberg trick tells you that if you write this sum countably many times, and this is, of course, if you put the brackets like this, it's just T to X times omega. But you can also put the brackets this way, and then this is isomorphic to M plus T X times omega. And that says that in this, if you look at this resolution of R, and these are just in at T, as in the condition T3. So what you can do, going backwards, you can add these some big number of copies of T to change the sum end into a real direct sum of copies of T. So the condition will be the same, except now that these terms of the co-resolution will be in sum T, direct sums of copies of T. So that's the first trick. So that's number one. And then you use this for the first part of the lemma, showing that each tilting module is equivalent to a good one. The second thing is to use the Eilenberg trick, iterate the trick backwards. And then what you get you go back, and eventually what you get is that this expression will be, you get something like this, r to t to x0, t to xn. And then it's easy to see that t is equivalent as a tilting module to any direct sum of copies of t. So for the tilting module, you can just say sum up these elements, and this will be an equivalent tilting module, and it will be good because here this is a summand already of t prime. Say, let's call it t prime. So using Eisenberg's trick, you can easily prove the or iterate. You can prove the first claim, and then the second thing is similar. Again, you can use the Eilenberg trick to have the sum resolution, and then you don't go backwards, but you go forward, and you get you can replace the in this co-resolution, you can replace these indices by finite ones using the fact that the well, gradually you use only finitely many finite number of copies, and the cos-syzygies are finitely generated, and you use induction. So this is easy an exercise, but it's good to know, because so in other words, up to equivalence, you just care for good ones, and the classic ones are always good. So this is like that's just the general picture. Now let's look at the tilting classes, which are which is the thing that you can eventually classify in the commutative Noetherian case, while it's very hard. It seems to be out of reach to classify the tilting modules themselves, because they are just big. And the tilting class is the usual definition is that is the kernel or intersection of the kernels of the covariant X functors from I1 and more of induced by T. So that's the right tilting class, or just tilting class. And the left tilting class is the kernel of the contravariant first X, or again, intersection of infinite ones is the same in this case. So the notation would be like this. So this is like the right perp of T, or infinite right perp, and this is the left perp infinite of one first. It doesn't matter. And the lemma says that these classes are defined, of course, via T, though this is the perp of T, and this is like the double perp of T, if you want. But they can be defined also in a more homological way, in the sense that you can describe them by resolutions and co-resolutions. So A is the class of all modules which have an at T co-resolution of length at most n. And we know R has one, so R is, of course, in A. And this property of R, given by the condition T3, is actually characterizing all modules in the left tilting class. That's what the lemma says. And the and the right tilting class can be characterized as the modules possessing an at T resolution, and that can be infinite, of course. And the important, but the easy thing, again, it's an easy exercise which you can do. I won't do it here. That the intersection of these two tilting classes is the important thing, the at T. So one inclusion is trivial, and the other is some work. Now, what are the classic theorems from tilting theory? So maybe the most famous one that motivated this is the theorem of Miyashita, which generalizes the Morita theorem. Maybe I should draw a picture. I think everybody knows the Morita theorem, which says that when we do the does equivalence of module categories look like? So you have two module categories of two rings R and S, and equivalence means that there's two functors which composed are naturally isomorphic to identities on the respective categories. And Morita proves that these are representable functors, and in fact they are represented by a module, by Hom and tensor product. And this module P, say, is a progenerator, finitely generated projective generator. So each equivalence of module categories looks like this, and vice versa. If you have a progenerator, use these two functors, then you get the module category of the progenerator equivalent with the module category of its endomorphism ring. So that's the classic stuff. And the tilting version of that, and we know that classical zero tilting module is just a progenerator, so that fits into that picture. It's exactly the case. And this just says that if you take a classical n tilting module, then there will be a similar picture, except that so now we'll have a t here, except that there will be more. Okay, so still I will have to draw a better picture here. So this category, there will be not a single equivalence, but a n+1 equivalences. There was one in dimension 0, so there are n+1 in dimension n. Namely, the two categories. So you have T classical and tilting. And then you have this category mod R and the category mod S, where S is the endomorphism ring of R, of T, sorry. So, and now this splits into pieces, n+1 pieces, and the same here. And the corresponding pieces are equivalent. So there's an n+1 tuple of functors. The first one is just a home functor, as in the Morita setting, and the tensor product. But there are other functors, and the last one is x r n t dash tor dash st. So this is the 0x first, etc., up to the nth one. The n+1 is 0. And the classes here are just those where the other functors vanish. So that's written here. So if you use the if you are in the I step, so the xi and tor I going back, then the classes on the right, the boxes here on the right and left, are just the intersections of the kernels of the other functors. So that's Miyashita. And this is in fact a stockwise version of a further theorem by Happel and Ricard, which says that the derived, essentially it catches the property that the derived categories of T, derived categories and derived category of R and S are triangle equivalent. Now there's a version of this theorem by Bazzoni, Montes and Tonolo, which tries to generalize this to good tilting modules. And it works to some extent, except that now the left classes are okay, but for the right classes you have to make them smaller by intersecting them with kernels of certain functors. Namely, you take the kernel of the total derived functor of the tensor product, IS or T over S, and then you take those which have no homomorphisms from the derived category to these from these modules, from these complexes to X. And so this is smaller, and you need a good tilting module for that. And again, this is a Stokewhite version of a theorem which says that the derived category of R and is equivalent as a triangulated category to the localization of the derived category of S. So it's not that nice, and maybe it's not that useful as in the classic case, because there you don't have to make things smaller. And the price also that you pay here is that you have to take good tilting module. And if you remember my argument that any tilting module is equivalent to a good tilting one, I have to enlarge the tilting module. I have to take some big sums. And that, of course, makes the endomorphism ring huge. So the point of this is once you replace the tilting by a good one, then you enlarge the endomorphism ring. So this category is this is a huge ring. So it doesn't work that well as in the classic case. I don't know of any application of this result in the structure theory of modules, while this result is used really a lot in finite dimensional algebras. Okay, so let's now come back to the point why we need infinitely generated modules. So the lemma which says that, and I will prove it in a minute, it says that if you have a strongly finitely presented module over a commutative ring, which has projective dimension at least 1, finite, then the xn functor Tt is non-zero. So it will never satisfy condition T2. And as a corollary, of course, of this is that if you have a classical tilting module over a commutative ring, it's necessarily projective. So it's a trivial setting. So why is that? So we had a proof of this result with David Pospišil, and which was more complicated, but the referee of the paper provided a nicer proof. So this is a proof to an unknown referee, or update of our proof by an unknown referee. Maybe the referee is in this room, so I would like to thank him. But anyway, it's not so. So what you do, essentially, you have a strongly finitely presented module. So its projective dimension is the maximum of projective dimensions of the localizations in maximal ideals. So there's you take the maximal ideal where the projective dimension is attained. So then if you localize the module, it will satisfy the same condition because the localization is just computed in this way. And so we can assume without loss of generality that the ring is local. So we can restrict to local rings by this simple trick, under the assumption of strongly finitely presented, of course. Now, and then the advantage is that once you are in the local setting, you have projective covers of finitely generated modules. So you not only have a projective resolution, but a minimal one, minimal free resolution, which is the iteration of projective covers of the modules, the syzygies, etc. So the differential, maybe I should draw this. So so this is the tilting module, which is free, minimal free resolution. Length n, and the differentials are it's noted here by d. So this is d1, etc. This is dn. Right. So that's the f. And of course, the differential, because it's given by a projective cover, the image dk of fk lands in the radical of the free module. So what does it mean? Now you use the fact that this xn functor is right exact because the xn plus 1 functor is 0. And you apply this epimorphism of t onto the t by the m times t. And this will induce a surjection, because that's a surjection of that thing onto that thing. And so it's enough to prove that this is non-zero, yeah? But you can just compute it. This xn tor of these two is just the x1 tor of the n minus 1 syzygy, which is somewhere here. But that, of course, is the x of that x1 of that syzygy with t by mt is just computed as all homomorphisms from this to that modulo those that factors that extend through the dn. But there's nothing that extends through dn because dn maps into the maximal submodule and therefore it maps to 0 here. So the x is actually a hom, and this hom is always non-zero because that's non-zero, and that's what was supposed to be proved. So this is the easiest proof I've seen. We had a more complicated one, but it's similar. So anyway, so probably you have people in commutative algebra know this. So there's no tilting unless you have an infinitely generated module. Okay, now let's look at an example where you see some concrete picture. So take a Dedekind domain with a quotient field Q and take a subset of the maximal spectrum, so some set of maximal ideals, and you define this. You can define this module which lives between R and the quotient field, which is just, well, it's defined using the fact that the factor, this injective module, is isomorphic to the torsion injective module, is the direct sum of all indecomposable injectives over all maximal ideals, well-known fact. And you just, what you do, you take this at P, and you just take the primes which are not in the set P, and you lift them up in the projection. So this will give you some actually subring of Q, which is between R and P, and has this property is uniquely determined by this. And now it's easy to see that if you take this Trojan-free module plus this divisible module, this is a tilting module, and the tilting class are just turns out to be those modules which are divisible by all primes, which you outside the set P. So that's easy to see, just you verify conditions T1, T2, T3, but what is less easy to see, at least at this point, is that these are the only tilting modules up to equivalence. So all of them except for the choice where P is the whole spectrum are projective dimension 1 and infinitely generated, and of course the trivial case is just the regular modules. Okay, so what about this other result which I mentioned, that the tilting modules or classes are finite type? So the theorem says that however big a tilting module you take, you can always, and with the tilting classes left A, right B, you can always find a subset of the class A, and it need not be finite, but it's a set of strongly finitely presented modules, so small modules, which replaces T in the definition of the right tilting class. So in other words, the class B, which is T right perp, is actually the right perp of the set S. And the largest choice, of course, is the all finitely presented modules in A, in which case you get actually that the class lives in the limit closure of that. So the class contains S and is inside the limit closure of S. So it kind of gives you more information. In fact, the class consists of transfinite extensions of modules from S. And the proof is, this is a hard result. It's in 4 papers, long papers, and was proved about 15 maybe years ago. And it's difficult because you have to first reduce to countably presented, strongly countably presented modules. And that's done by some set theoretic homological algebra, separately for regular and singular cardinals by induction on the projective dimension of the modules in the class A. And then there's a subtle point from countably presented to finitely or strongly finitely presented, which uses Mittag-Leffler condition, and that was done by Dolores Herbera and Silvana Bazzoni, while the first part was by me and Jan Šťovíček. So what are the consequences of this result? So first of all, the tilting classes are definable in the sense, well, closed under direct limits, pure submodules and products, but maybe the more usual meaning of definable means you can axiomatize the property of being a module in the class by a set of first-order formulas in the language of theory of modules. Namely, the point is, let me go back, that this condition for a single strongly finitely presented module is just can be expressed by extending a map to a bigger module, both finitely presented, and the existence of a map can be described by a formula, and the extension also. So it's the X vanishing is just describable by a first-order formula, and then you have a set of first-order formulas, and that's just gives you the definable class. So these classes are, well, interesting even from the model theoretic point of view. And the correspondence also tells you, or the finite type result, that actually though the tilting modules or classes are big, they can be captured by subclasses of small modules, namely so-called resolving subclasses, subcategories of strongly finitely presented modules. And resolving means that they contain all finitely generated projectives. They are closed under extensions and direct summands, and they have this property that if B and C are in the class, that A is in the class. So it's the kernel property. And the classification then says that you have a correspondence between n-tilting classes, or right n-tilting classes, and the resolving subcategories, given in the easy way. So given the resolving subcategory, you just take the perp. And going back, you just take the left perp of the tilting class and just take all the strongly finitely presented modules there. So it's quite easy to compute this correspondence. So if you look back at the Dedekind domains, so there should be some set of strongly finitely presented modules behind the scene for any tilting module, and it's really easy to see. If you have the tilting module defined by a subset of the maximal spectrum, then the strongly finitely or finitely generated modules needed are just the cyclics, which are for the primes, maximal ideals where the primes are not in P. And that's why the tilting class was just a class of P divisible, modules divisible by P from P not in P, because this is the small set behind the scene. Okay, so let me do an application of this to something which is maybe not expected to be related to tilting, and that's the finitistic dimension of Ivanaga-Agharnstein rings. Again, this is not a new result, but I think I like it, so maybe I hope you will enjoy it too. So what are these Ivanaga-Agharnstein rings? So it's a generalization of n-Agharnstein rings from commutative setting to non-commutative, so they are left and right Noetherian, and both the left and the right injective dimensions of R are equal. So 0 Agharnstein is just quasi-Frobenius, for example. That's not necessarily commutative, of course. And there are two dimensions defined for any ring, so in particular for Ivanaga-Agharnstein, the big finitistic dimension, which just denotes the supremum of the projective dimensions of all modules that have finite projective dimension. Remember, global dimension is the supremum of the projective dimensions of all modules. Here you restrict to those that have finite projective dimension. And the similar thing, little finitistic dimension is the same thing, except you further restrict to finitely generated modules of finite projective dimension. So this is the terminology going back to Bass. And the theorem which I'm going to prove is that if you have an n Ivanaga-Agharnstein ring, then both dimensions are equal, and they are equal to n. Not surprisingly, but they're equal, that's the point. So this is the first and the second finitistic dimension conjectures hold in this setting. So the proof. So it's, if R is n Ivanaga-Agharnstein, so this is known as actually an equivalent definition, that all modules of projective dimension at most n is the same as injective dimension at most n. And this P is the class of all modules of bounded projective dimension is just bounded by n. Yeah? So there's a bound of projective dimensions of all modules of finite projective dimension, namely n. So the big finitistic dimension is known to be n. Now let's take the strongly or finitely presented or finitely generated, in this case, modules in this set of class of all modules of bounded projective dimension. So what is the idea of the proof of the finitistic dimension conjecture? It is that you will show that this class is actually a tilting class of some possibly infinitely generated tilting module. And then you will use the finite type. So how will you use the finite type? The finite type will you give a set, will replace this T by a set of finitely generated modules giving the same tilting class, right tilting class. But then P is the double perp of that. And as I said, this double perp is just transfinite extension, so it cannot have a bigger projective dimension than this one, and therefore the two dimensions are the same. Once you prove that this is a tilting class. So how do you prove it? You just have to have some idea what would be the tilting module here, and you just take the minimal injective co-resolution of the regular module, which looks like this, the injectives I0 to In, and sum these injectives up. And this will be the tilting module. So note that this is very infinitely generated, even in the commutative case, of course. Injectives are rarely finitely generated. So we have this, we will prove that this, okay, so this is a tilting module because it's injective. So, and this is condition T3, and the X vanishes because it's injective, so it's trivial. So let's look at what are the left and right tilting classes. So first, we know that when they intersect, they give you at T, and we know that at T consists of the injectives, because T is injective, and the ring is Noetherian. We will show that it actually is equal to the class of all injective modules, because if you take an arbitrary injective module and any module in B, we know that it has an at T resolution by the characterization, by this lemma at the beginning, So if you look at the syzygy of B, of the module B in this resolution, you can compute that for any injective I, this x is the same as the xm plus 1 of the syzygy and syzygy. And this you can do by dimension shifting because RT is in the injective. So you can, you're in the injective, yeah, so you have a co-resolution. And then this just says, this must be 0 because the injective has bounded projective dimension by n. So this is 0. So we have proved that any injective lives in the left perp of B, and therefore the injective is in A, and therefore it's in RT. And now the finish is very easy. So you know that the A is the class of all modules which have bounded co-resolution by the modules in the class in RT by this general theorem lemma. And these are exactly the modules of finite, of injective dimension at most n. But these are also, by this remark at the beginning, the same as P. So we have proved that A is P. So P is a left tilting class of a tilting module, namely of this guy here. And okay, so the proof is finished. So the only difficult thing in this is that you have to use the fact that it's finite type, yeah, which you don't see a priori. Otherwise, it's just easy arguments. Okay, so let's look back at this tilting module that we used here. So because you may know that this finitistic dimension conjecture is still open for Artin algebras. The part that says that the little finitistic dimension of an Artin algebra is finite, this is not known. There are many cases where it's proved, but it's still one of the major open problems in finite dimensional algebras. So let's look at it a bit. Let me use a brief recap of this. So what does it mean that the finitistic dimension conjecture holds, that this little finitistic dimension is finite? This is just saying that there's a greatest element in the partial order of tilting modules, which are partially ordered by the inclusion of the left tilting classes. And this greatest element is then denoted by TF for the finitistic dimension conjecture. And the point is that the finitistic dimension is just the projective dimension of that particular tilting module. So in our case, this TF was just this injective that we guessed at the middle of the proof, and then it worked. The interesting thing is that okay, so we would like to see whether there's this greatest element and what does it look like. So if the conjecture holds, which is expected to be the case, but then there's a tilting module behind. The interesting thing is that even for Artin algebras, this tilting module, when it's computed in various cases, is not finitely generated in general. So this is not the tilting module people in finite dimensional algebras are studied. You have to go out of the world of finitely generated modules, as we did in the case of Agharnstein rings. And it's even known when exactly it is finitely generated. For this you need that the class of all finitely generated modules of finite projective dimension is a covering class in small mod R. So this is called the contravariant finiteness. This is a result of Auslet and Reiten. So essentially, to answer the question, so to answer this conjecture, one way to answer it is to show that there's a maximum element and maybe even compute what it looks like, which in all cases when this was proved, it's possible to compute, but it's very hard. So I believe that if the conjecture is true, then one way to prove it could be by computing, by finding some extra properties of this tilting and showing, well, computing it, finding it somehow. Yeah. But this is still open, and it's open for maybe 40 years or 50. Anyway, so since I mentioned this covering class, I would like to briefly finish with the relation of of tilting and approximations of modules, which is very direct. So if you know the notions, it's really easy. So I will just repeat recall the definitions in the terminology of Inox rather than Auslander, who uses different terminology, but same thing. So precovering class is just a class which gives for any module precover. So if the class is C, it's a C precover, which is a homomorphism from an element of the class to the module, which is like the best approximation of the module in the class, in the sense that whenever you try to approximate by a different module, a different map, it will factorize, not necessarily uniquely through this approximation F. And if this map is surjective and the kernel is in the perp of C, this is called a special C precover. And if the map is right minimal, meaning that if you take F again here, then the only factorization is through an automorphism, then this is called a C cover. And the C covers are unique. They are summands of any C precovers, as we know. So for the case C is the class of our projective modules, these are exactly the projective covers. That's just a generalization of that. And C covers, if the class contains the projectives, C covers are always special. That's why the special are so important. And if all modules have a C cover, C precover, special C precover, and C cover, then the class is called special precovering, covering, etc. There's also the dual notion, which we will need tomorrow. But the relation to tilting is given by probably the nicest in the one-dimensional case. So what are the one-tilting classes of modules? The right ones. They can be characterized from the approximation theory point of view as the special pre-enveloping torsion classes of modules. So if you have a special pre-enveloping class in the sense I defined in the previous slide, and it happens to be a torsion class, it's because it's a tilting class, and vice versa. So this is, I think, interesting, and we will use it later on. And there's a version in the n-dimensional case which is not that nice, which says that the n-tilting classes, the right L-tilting classes, are again special pre-enveloping, but this is not enough. And they are closed under direct sums, direct summands, co-resolving, and the left perp of those classes is of projected dimension at most n, if we are dealing with an n-tilting class. So okay, so there are many references. Each of the theorems comes from some paper. Some of them I mentioned, but everything is in this book that I wrote with Rüdiger, so I'm not going to, though we don't claim we proved all of this, but it's there. While the results I will speak about tomorrow and after tomorrow, I will give detailed references because there are more recent results and there are papers covering them exactly. So thank you for your attention.